Hello friends. So today we are going to solve the questions from modern physics, and these questions are from the year 2022. 4 questions. 2023, 3 questions, and 2024, 1 questions. And all these questions are from the advance. So all these questions are from the advance. So the first question, it was asked in the year 2022, and it states that the minimum kinetic energy needed by an alpha particle to cause the nuclear reaction nitrogen plus helium giving us a hydrogen plus oxygen in a laboratory frame is N in mega electron volt. Assume that nitrogen is at rest in the laboratory frame and the masses of nitrogen, helium, hydrogen and oxygen can be taken as 16, 4, 1 and 19 respectively. AMU, where 1 AMU is equal to 930 mega electron volt, then the value of N is. So N is nothing but a representation of our kinetic energy. So we are supposed to find out what will be the kinetic energy or minimum kinetic energy. And that is for our alpha particle. Okay, alpha particle is nothing but our helium particle. Okay. So first of all, we are going to calculate the Q value of the reaction. Q value of the reaction. So we can, with respect to the mass defect, you can say that this Q value will be equal to our initial mass minus final mass and multiply by our 930. So initial mass will be with respect to our reactants, and the final mass will be with respect to our products. So we can write that our initial mass which is our Mi, and that will be equal to mass of nitrogen plus mass of our helium, and both values are given to us. So we can say our initial mass will be equal to nitrogen is 16.006 plus helium is equal to 4.003. This gives us 20.009 AMU. Similarly, we can write for our final mass. Final mass will be equal to mass of our hydrogen plus mass of the oxygen. So once again, substituting the value, we get our final mass of hydrogen. It is given as 1.008 plus for oxygen it is our 19.003. So this gives us 20.011. Therefore, mass difference, that is of delta m, will be equal to our initial mass minus final mass. So which comes as 20.009 minus 20.011, and this will be coming as minus 0.002. Now we can find out our Q value. We get our Q will be equal to delta means our minus 0.002 multiplied by 930. This comes as minus 1.86 mega electron volt. So here we get that the value of Q is negative, or we can say value of Q is less than 0. So from here we can say that it is an endothermic reaction. Endothermic, and because of that it requires a kinetic energy input. Requires kinetic energy input. In this case, the kinetic energy of the helium. And now we are going to find out the minimum kinetic energy. So minimum kinetic energy, let us say this is our K minimum, which is nothing but our value of n, which is according to the question. And it states that our target nucleus is at rest. Nitrogen is at rest in the laboratory form. So our target is of nitrogen, which is at rest. So we are given that our target nucleus is at rest. Is at rest. Okay. So our K minimum will be equal to minus Q multiplied by our mass of the projectile. In this case it is alpha particle. So let me write the formula first of all. This will be mass of projectile plus mass of target. Target is of helium, and whole divided by mass of our target. So we substitute the values. Q we already know. This will be equal to our minus Q will be giving us plus 1.86 multiplied by mass of the projectile is our helium, that is 4.003. Target is our nitrogen, and it is given as 16.006 divided by 16.006, and this will be giving us 1.86 multiplied by 1.25. So therefore we can write our K minimum will be equal to 2.33 mega electron volt, which is nothing but value of our n. So it comes as 2.33 mega electron volt, 2.33. Next question. It states that it was also asked in the year 2022 advance, and it states that the binding energy of nucleons in a nucleus can be affected by the pairwise Coulomb repulsion. Assume that all nucleons are uniformly distributed inside the nucleus. Let the binding energy of the proton is EPB and binding energy of neutron is ENB in the nucleus. Which of the following statement is or are correct? Okay. So basically we have to find out the first four options are, we have to go and find out the difference between the two, and last option is basically how the binding energy of proton varies when the beta decay is taking place. So in the question we are given that we have our proton, and so this is given as binding energy of proton, and then we have our E and B, which is binding energy of neutron. Neutron? Yeah, neutron. And it says that only the Coulomb repulsion is affecting the binding energy. Okay, so we have to remember this thing. So let us check these options one by one and try to find out which of the options is correct or incorrect. So let's start with option A. And we are going to find out the difference in binding energy and the proportionality between the two. Okay. So in this case we are supposed to find out the difference between the two. Okay. And here we have to remember, let me first of all write the statement. So in this case we have to remember that the Coulomb repulsion affects the proton binding energy. You can say our Coulomb repulsion affects proton binding energy. Proton binding energy. Okay. And or it also says pairwise. Okay, let me, here it is written as pairwise. And so the option A it says that the difference between the binding energy of proton minus the difference of our neutron is proportional to Z multiplied by Z minus 1. Okay, where Z is the atomic number. And this we can say is I think this is can be expressed directly in the form of the formula. So in this case, let us, you can say, write the expression for the binding energy, and in this binding energy, for the time being, let us consider that there is no repulsion. Okay, then we can include the concept of repulsion also. Okay, because otherwise it will be a little difficult to sort it out. So we start with the that total binding energy without repulsion. And the binding energy formula is given as Z multiplied by mass of proton plus A minus Z mass of neutron, and we have m of x, and this is whole multiplied by c square. And this equation is for a hypothetical element which can be represented as A of Z. Now let us consider the repulsion. So we can say that for repulsion, number of the proton pairs and they can be written as ZC2. So based on this, we can write the repulsion energy Therefore, we can say that repulsion energy can be written as proportionality will be our z minus 1 divided by 2, and this comes 1 upon 4 pi epsilon naught, and our E square divided by R, and here R is the radius of nucleus, and we are having proton as well neutron and their difference in energy. Therefore, we can say the binding energy of proton minus binding energy of our neutron will be proportional to z minus 1. So it means our option A is correct. A is correct. And we also know that the general formula for our radius of nucleus, that is R, is equal to R naught A raised power 1 by 3. So in this case, so let us call this equation number 1. So if in equation number 1 we substitute value of R, therefore we can say that from equation 1 we can write, if we can assume, because it is based on the proportionality, so if we can assume that this part is more or less constant, so this will be proportional to 1 upon R, and we substitute value of R, which gives us proportional to 1 upon R naught A 1 by 3, and this R naught is constant for all the, you can see, all the atoms. This radius value is constant, so therefore we can say it is proportional to A raised power minus 1 by 3. Therefore we can say from here that for our difference proton minus neutron, binding energy is proportional to A raised power minus 1 by 3. So we have our option B is also correct. B is correct. And finally, third option is that their subtraction is minus. Okay. And we can say that our repulsion will be with respect to our can say protons experience Coulomb repulsion which reduces their binding energy. Compared to neutrons. Therefore, we can say that binding energy of our proton will be less than binding energy for neutron, or from here we can say that binding energy of our proton minus binding energy of our neutron will be less than 0. Yeah, less than 0. So negative. Therefore option C is incorrect. C is incorrect. And now we come to the option D, and it states that for the beta decay our proton binding energy increases. Okay. So we know that whenever there is our beta plus decay, it reduces the proton number, reduces the proton number, or we can say our Z, further reducing our Coulomb repulsion, reducing Coulomb repulsion. So there will be less repulsion, so because of this we can say high proton binding energy, high proton binding energy. So therefore our option D is correct. D is correct. Next question. It states that it was also asked in the year 2022, in a radioactive decay chain reaction, thorium nucleus decays into a polynomial nucleus. The ratio of number of alpha to the number of beta negative particles emitted in this process is. So we are given that we have a parent nucleus, that is our thorium. So we are given that we are having a parent nucleus, and that parent nucleus is our thorium, and it decays into a daughter nucleus, and that daughter nucleus is our polonium, and that is 14 and 84. So we have to find out the alpha particle as well as beta negative particles. So first of all, let's find out what will the change in the mass number and atomic number. So we can say our change in mass number let us suppose we call that delta A is equal to 230 minus 214. and which comes to as a 16. And then we can find out the change in atomic number. That is delta Z will be equal to 90 minus 84, which comes as 6. And now it says that we have alpha particle and we have a beta minus particle. So for according to the decay rules, you can say from decay rules, and for our alpha particle, we are having that our mass number A, it is reduced by 4, and our atomic number, that is our Z, it is reduced by 2. And for our beta minus, particle, our mass number, it remains unchanged, and our atomic number is increased by 1. So now we can just find out the corresponding parts. So let us assume that the number of alpha particles that are during the decay, the number of alpha particles emitted are, let us suppose, as x, and for beta negative particle, let us assume that they are y. Therefore we can write that our change in mass number we can say that our 4x will be equal to 16 and x will be equal to 4. And change in atomic number, we have our 2x minus y is equal to 6. X we found out is our x we found is our 4. So this gives us 8 minus y is equal to 6, giving us that the value of y is equal to 2. And we are required to find out the ratio, that is our x upon y. So we can say our ratio, that is number of alpha and we have number of beta negative, or we can say our x upon y. So this comes as 4 upon 2, giving us 2. So the final answer is ratio is 2. Next question. It was also asked in the year 2022, and it states that when a light of a given wavelength is incident on a metallic surface, the minimum potential needed to stop the emitted photoelectrons is 6 volt. This potential drops to 0.6 volt if another source with wavelength 4 times that of first one and intensity half of the first one is used. What is the wavelength of the first source and the work function of the metal respectively? Okay. So in this case we are given that we have two wavelengths and the respective you can say stopping potential is given as 6 as well as 0.6. So we can say that for wavelength our lambda 1, we can say that our stopping potential that is our V1 is our 6 volts, and for wavelength lambda 2 stopping potential let us suppose is our V2, it is 0.6 volts, and we know the general formula for our photoelectric equation. We can say that photoelectric equation, and we can write that our Hc upon lambda is equal to our work function plus our stopping potential. Okay, this is V. Now we have two wavelengths, so we can just divide into two parts. We can write this will be equal to Hc upon lambda 1 is equal to phi plus E times V1. Second one becomes Hc upon lambda 2 is equal to phi plus E times V2. And we are given the relationship between lambda 1 and lambda 2, that is our 4 times. Therefore, we can write that we substitute lambda 2 as 4 times lambda 1, we get this as Hc 4 times lambda 1 is equal to phi plus E times V2. And we also know that our energy E, or we can say photon energy, that is our E is equal to 1240 and lambda, and this is an electron volt, so here lambda has to be in nanometers. Therefore, we have two wavelengths, and based on this we can write the equation of photon energy. Therefore, we can say, or rather in terms of our given stopping potential, we can say that our E V1 is given as 6 electron volt, and our E V2 it is given as 0.6 electron volt. So we can write the respective equations, that our Hc upon Hc is our 1240. So we can say this our 1240 upon lambda 1 is equal to 5 plus this is our 6 volts. Second one becomes our 1240 lambda 2 is equal to 5 plus 0.6, and we subtract these two equations. So 1240, sorry, here it is 4 times lambda 1. Therefore we subtract them and we can take 1240 as common. So we get this as 1 upon lambda 1 minus 1 upon 4 times lambda 1. 5 and 5 cancels out and this comes as 6 minus 0.6, which is giving us 5.4. And on the left side we are going to get this as our 1240 multiplied by 3 by 4 multiplied by 1 upon lambda 1 is equal to 5.4. And from here, now it is a simple calculation. Lambda 1 will be coming as 1.72 into 10 to the minus 7 meters. Okay, so this is value of our lambda 1 and first source, and we need to find out our work function. Therefore we can say our work function that is our phi will be equal to 1240. We can use any of the equation, lambda 1 minus 6, and this comes as our 5.4 minus 6, giving us minus 0.6 electron volt. 1 second. No, my mistake. 1 second. So let me write 1240 by lambda 1 is equal to 5 plus 6, and lambda 1 is our, so this gives us 1240 1.72, and it has to be nanometers. Yes, so this comes as 172.2 is equal to 5 plus 6. Now it will be coming correct. So on the left side it comes as 7.2 is equal to 5 plus 6, giving us phi is equal to 7.2 minus 6, which will be equal to 1.2 electron volt. So this is 1.72, 1.2. Option A is correct. A is correct. Next question. It was asked in the year 2023, and it states that a hydrogen-like atom has an atomic number Z. Protons emitted in the electronic transition from level 4 to level 3 in these atoms are used to perform a photoelectric effect experiment on a target metal. The maximum kinetic energy of the photoelectron generated is 1.95 electron volt. If the photoelectric threshold wavelength for the target metal is 310 nanometer, the value of Z is, various constant values are given to us. So we are given the transition. So we are given that we are having a transition, and that transition is the value of n is 4 to value of n is equal to 3. We are also given the maximum kinetic energy of the photoelectron. Maximum kinetic energy of photoelectrons, that is our, let us suppose we call this as K max, and this K max is given as 1.95 electron volt. And we are also given the threshold wavelength, that is lambda naught, is also given to us. Threshold wavelength, that is our lambda naught, it is given as 310 nanometer, and various value constant is also given. So therefore we can find out the wavelength, and from the transition, during the transition process. And so let us find out first of all the energy of the emitted photon. Energy of emitted photon, if that is given as E, then this E will be equal to RHC Z square 1 upon N1 square minus 1 upon N2 square. And except Z, all the values are known, except Z and E, all the values are known to us. Therefore we can say our energy E will be, RHC is given to us 113.6 Z square, value of N1 and N2 is known to us, so this comes as our 3 square minus 4 square. So therefore we get that our energy is equal to 0.661 multiplied by Z square electron volt. And now we can use our photoelectric equation. Photoelectric equation, and which tells us that the maximum value of the kinetic energy will be equal to energy of the photon minus the work function. And phi, that is our work function, can be calculated using our threshold wavelength. So we can write that our phi will be equal to hc upon lambda naught, and this comes as our 1240 and 310 in nanometer, giving us 4 electron volt. And from here K max and phi, we can find out our energy of the photon. Therefore we can say that our K max is given to us 1.95 is equal to our energy of photon minus work function. This gives us that the value of E is 5.95 electron volt. and we are going to use this particular relationship and get the value of Z. Therefore, we can say that our E is equal to 0.661 times Z square. This gives us 5.95 divided by 0.661, and this is equal to Z square. And from here we can say this Z square approximately comes equal to 9, giving us that the value of Z is equal to 3, which we were supposed to find out. Value of Z is our 3. Next question. It was also asked in the year 2023, and it states that the electric field associated with the EM wave propagating in a dielectric medium is given as 32x unit vector plus y unit vector sine of 2 pi 5 into 10 raised to power 14 t minus 10 raised to power 7 z divided by 3 volt per meter. Which of the following option is or are correct? So basically we are going to find out the components of the magnetic field in x and y direction and the polarizing angle as well as the refractive index. So first of all, let's find out from the given equation, because it is traveling in a medium, not in a vacuum. So we are going to find out first of all the velocity of the EM wave. Okay. So we can say wave speed in a medium and that is our V will be equal to omega upon k, angular frequency upon wave number. So we get our V is equal to, and omega is our 2 pi into 5 into 10 raised to power 14. Wave number is our 2 pi into 10 raised to power 7 divided by 3. And here 2 pi and 2 pi cancel out. This 3 comes as 15. So we can write this will be equal to 14 and this will be over 7, 8. And so we can write this will be over 1.5 into 10 raised to power 8 meter per second. So we know that the refractive index is the ratio of our light speed in the vacuum divided by light speed in a medium. So from here we can say the refractive index and which is given, let us suppose as n, will be equal to c upon v. Speed of light in vacuum, that is 3 into 10 to the power 8 and 1.5 into 10 to the power 8, and this comes as 2. So option D is correct. Correct. And next is with respect to our magnetic field components. And we know that our magnetic field in a EM wave magnetic field in an EM wave, suppose that is given as B, then this B is equal to 1 upon V multiplied by cross product of our k unit vector and our electric field. And we can say that our this wave is propagating in plus z direction. So you can say since the wave propagates in plus z direction, therefore from here we can write that our k unit vector will be our z unit vector. And let me write the given equation of our electric field. So we are given that our electric field is equal to 30, okay, let's multiply by 30 inside. So this comes as 60 x unit vector plus 30 y unit vector. So the electric field is also having two components, x as well as y component. Okay, and the secondary part is common to both for x as well as y. So this comes as 2 pi 5 into 10 to the power 14 times t minus 10 to the power 7 divided by 3 times z. And magnetic field will be equal to, like we said, it is 1 upon v. V we found out. So we can say that our magnetic field will be equal to 1 upon 1.5 into 10 to the power 8. And k unit vector is our z unit vector. Cross product, now we put the value of our electric field, that is our 60 x unit vector plus 30 y unit vector, and rest will be magnitude, which will be same. So this we get a sine of 2 pi 5 into 10 to the power 14 times t minus 10 to the power 7 divided by 3 times z. So we are going to find out their cross product, and z unit vector multiplied by x unit vector is going to give us y, and z unit vector multiplied by y unit vector cross product will be giving us minus of x. So we can write our magnetic field will be equal to 1 upon 1.5 into 10 to the power 8, and this comes as 60, and we have our y unit vector minus 30, and we have our x unit vector, rest will be our same, that is our sine 2 pi 5 into 10 to the power 14 times t minus 10 to the power 7 divided by 3 z. Now we can easily divide into components x as well as y. Therefore we can say that our x component, which will be our b of x, will be equal to minus of 30 divided by 1.5 into 10 to the power 8 sine of 2 pi 5 into 10 to the power 14 times t minus 10 to the power 7 divided by 3 times z. And this gives us that our x component will be equal to minus of 2 into 10 to the power minus 7 sine of 2 pi 5 into 10 to the power 14 times t minus 10 raised to the power 7 divided by 3, and we have this as z. Similarly, our y component b of y will be equal to, this will be 60 divided by 1.5 into 10 raised to the power 8, and this parameter will be same. So let me solve this 60 part only, and this will be coming as 4 into 10 raised to the power minus 7, and then we get the sign of 2 pi 5 into 10 raised to the power 14 times t minus 10 raised to the power 7 divided by 3 times z. Therefore, option A is correct. Option A is correct, and option B, this magnitude part is our maximum value of magnetic field, is wrong. And finally, we have find out the polarization, and the polarization will be our, you can say, tangent of theta, y component of electric field divided by x component of electric field. So we can say polarization angle theta and this is basically, we can write that the tangent of theta will be equal to electric field component in y direction divided by electric field component in x direction. So which is simply their magnitudes, that is 30 divided by 60, okay, because this is our y component and this is our x component. And we get that our tangent of theta will be equal to 1 by 2, which gives us that our theta is approximately equal to 26.57. So therefore, option C is also incorrect because it is 30. Option C incorrect. Next question. It was also asked in the 2023 advance, and it states that in a radioactive decay process, the activity is defined as A is equal to dN upon dt, where n of t is the number of radioactive nuclei at time t. Two radioactive sources S1 and S2 have same activity at time t is equal to 0. At a later time, the activities S1 and S2 are A1 and A2 respectively, when S1 and S2 have just completed their third and seventh half-lives respectively. The ratio of A1 and A2 will be. Okay. So here we are given that initial activity of both the sources S1 and S2 is same. So you can say that same initial activity, and this is true for our S1 and S2. Initial activity means at t is equal to 0, and it says that S1 completes 3 half-lives and S2 completes 7 half-lives. Okay. So we can say that S1 completes 3 half-lives, and after that its activity is given as A1, and we have our S2 that completes 7 half-lives, and its activity is given as A2. And we already know the general formula for the activity after n half-lives. So we can write that activity after time t will be equal to lambda multiplied by n of t. Okay, that is the number of radioactive elements at time t. And another formula is our that number of nuclei after time t is given as our n naught half raised power n. And from here, combination of both, we can write that our A will be equal to A naught 1 by 2 raised to power n. So we get our activity after n half-lives. Okay. So this is our activity after n half-lives. So now we have two samples S1 and S2. Therefore we can write that for S1, which is having 3 half-lives, and the activity is given as A1, initial activity is our A naught, and half-life is given as 3, that is the value of n is 3. So this gives us 1 by 8 multiplied by A naught. Similarly, we can write for S2. So for S2, we have our A2 is equal to A naught, and it is having a 7th half-life. So this comes as 128 times A naught. Now we can easily find out their ratio. Ratio, that is our A1 to A2, is equal to A naught upon 8, A naught upon 128, and this comes as our 8, and this will be our 128, giving us 16. So answer is 16. Next question. It was asked in the year 2024 advance, and it states that a particle of mass m moving in a circular orbit under the influence of a central force Fr, which is given as minus k of r, corresponding to a potential energy V of r, which is our kr square upon 2, where k is a positive force constant and r is the radial distance from the origin. According to Bohr's quantization rule, the angular momentum of the particle is given by L is equal to n times the quantization, या Bohr quantization, where this Bohr quantization is equal to h upon 2 pi. H is the Planck's constant and n is a positive integer. If V and E are the speed and total energy of the particle respectively, then which of the following expression is or are correct? So we are going to find out the velocity, radius, or the momentum relationship, which of them is correct. So we are given that there is a force, central force, acting on the particle. So we are given the central force that is of f of r is equal to minus k of r. and this is corresponding to a potential energy. You can say corresponds to potential energy, which is given as V of r is equal to kr square upon 2. And we are also interested in angular momentum, that is L, so we can also write the formula, or it is also given to us. So we can say from Bohr quantization rule, Bohr's quantization, it tells us that our value of L is equal to n times h, and this, let us call this as Bohr quantization, that is equal to h upon 2 pi. Okay, and if we know that particle is moving in a circle, so there will be a force acting to balance it, which we also call the centripetal force. So we can say that particle moves in a circle of radius r. Therefore, we can say that our mv square upon r will be equal to the central force, that is our k of r. So from here we can write that our v square will be equal to k upon m times r square. And okay, now we can use the Bohr quantization of angular momentum, or with simpler terms, let us write it as angular momentum. So we have our angular momentum, that is L, which can be written as mvr, and it is also given as h multiplied by the Bohr quantization. We substitute value of v, so we get our L is equal to, let me write from here, that value of v is equal to r times square root of k upon m. So we get L will be equal to m, and we have this as r times k upon m multiplied by r, and this will be equal to our r square square root of k times m. Therefore, we can say that our r square will be equal to L square root of km, and we can substitute value of L, so we get our r square will be equal to, L was our n multiplied by, and we have this as square root of km. One second. Yeah, it is only r square here, so option A is correct. Option A is correct. Now we can use the velocity equation. So we know our v square is equal to k upon m times r square. We substitute value of r square. This comes as k upon m multiplied by, we have this as n Bohr quantization and whole divided by k times m. And okay, now it is a simple calculation, and we can call this as our square root of k divided by m raised power 3 by 2. So we get our v square will be equal to n times Bohr quantization, and square root we can take common. Okay, so this comes as k upon m cube. So v square is equal to k upon m cube. Option B is also correct. Next, we are supposed to find out momentum as well as the total energy. And we already know that our momentum is equal to r square k times m. So we can say our L is equal to r square k times m. Which from here, let's multiply both sides by our mr square. So this becomes L upon mr square is equal to r square square root of km, and we have this as mr square. Here r square and r square cancel out, and we can take m inside the bracket. So this will be coming as square root of k upon m. So k upon m, option C is also correct. C is correct. And finally, we are supposed to find out E is the total energy. Okay. Therefore, we can write that total energy that is our E, sorry, not K but E, will be equal to K plus V. K is our half mv square, and equation for the V is given to us, that is half kr square. Now we substitute value of V square, or okay, let me use, first of all, we are given that our V square is equal to K upon m times r square. From here I can write my half m V square will be equal to half m times k upon m r square, and here m and m cancels out, so this comes as our half kr square. Therefore, our total energy E will be equal to, this comes as half kr square plus half kr square, which gives us that our energy E is equal to kr square. We can substitute value of our r square, and we get our energy E is equal to k times n h and divided by k times m. This comes as n Bohr quantization, and this comes as k upon m. So this comes as our, okay, here it is 2, which is incorrect. So option D is incorrect. Option D is incorrect. So this completes the advanced question for 2022, 2023 and 2024. Thank you.